webinar, which is on 3D printing at the point of care and its impact on ideation and medical prototyping. Today, we'll have three wonderful speakers that will join us, including Dr. Justin Bird, Dr. Alexandra Mericli, as well as Dr. Karthik Tapa. A little bit about our organization. Our webinar is hosted by the team at RSNA, which is the Radiological Society of North America, which has members throughout the world and hosts one of the largest radiology conferences in the world. The 3D Printing Special Interest Group is hosted by the RSNA, and our mission is to promote the highest level of quality in 3D printing in medicine through collaboration, education, and research, with a focus of working with radiologists as well as other physicians and allied health in this area of interest. You don't have to be a member of RSNA to join the 3D Printing Special Interest, and you can join through our website and have access to all the activities, including the subcommittees which focus on education, appropriateness criteria, quality assurance in 3D printing, as well as outreach. And once you join, you have access to our community page and you can become a member to any of the subcommittees. And we are very excited to introduce our CME meeting coming up this April on medical 3D printing. It's going to be hosted in Chicago. We'll have wonderful speakers that go through the indication of 3D printing, quality assurance in the process of at point of care 3D printing, as well as reimbursement and other areas, including talks from the FDA. Our registration is open and you can join us anytime. Without further ado, let me introduce our presenters today. We have Dr. Justin Bird, who is Associate Professor in the Department of Orthopedic Oncology at MD Anderson. He specializes in the treatment of complex spine and pelvic tumors with an interest in 3D and computer-assisted technology. He also serves as the Director of the Learning Cancer Outcomes Research Program, the Surgery Innovation Safety Officer, and Director of the ADS Lab. We also have Dr. Alexandra Mericli, who is Associate Professor in the Department of Plastic Surgery at MD Anderson, and he specializes in all aspects of reconstructive surgery in the breast, head and neck, and trunk. Importantly, also, Dr. Mericli serves as the Medical Director for Perioperative Surgical Services and is a champion in value-based care. Our last speaker, Dr. Karthik Tapa, is a biomedical engineer with the 3D Printing and Advanced Visualization Lab at MD Anderson, and he has experience in 3D model optimization, CAD design, and bioprinting, as well as facilitating prototyping. And without further ado, our team for today.
Hello, everyone. Are you able to see the screen?
Yes.
Perfect. Okay. Well, thank you, Dr. Santiago, and thank you to the Society for having us. Looking forward to the talks and the conversation. I'm going to just share some of my experiences with some innovative technologies and how this is impacting orthopedic oncology. First, I'd like to thank my team. I am fortunate to work with a great group here at MD Anderson in the orthopedic oncology department, as well as our collaborators in plastic surgery and then the rest of the surgical specialties. These are my disclosures. I did want to start just by way of introduction, sharing some of the kind of experiences that I've had that have led me to be interested and get involved in these technologies and applying them to our patient challenges. I started out in my medical training at Mount Sinai in New York City And during that time, I had a chance to travel as part of a medical mission to Malawi in the southern part of Africa. And that's where I was exposed to something called Pott's disease, which is tuberculosis of the spine, and decided that I wanted to do spine surgery in addition to the orthopedic oncology that I was planning to do. I also, at that time, started to realize how important the technologies we were using in my residency and my medical school training, how important they were, and how many other places in the world didn't have these technologies. And so really started to think through the innovative process and how I could be involved in that. And then I spent a year after my residency in Liberia, and so more of the same in a low resource environment, making do with the basic technologies, and realizing again how important technology is in the process. And then after leaving Liberia, I came to MD Anderson for fellowship, and I've been here on faculty. And just to show you some of these pictures and contrast the environment. So on the left, you have a number of the photos from my experience in Liberia, and you can see an OR room that we were using every day, and we have some old equipment that was donated. And I found these pieces of equipment in warehouses that were on the campus, and brought them out and started to use them and teach people how to use them. You can also see us doing some surgeries here in that environment. And I'm not sure if this shows up well in the presentation, but a dark room with a single light here. And so some of the just basic things made it difficult. We had trouble for a few months with our x-ray machine, so we didn't have an x-ray machine working in the hospital, and when we did, it was hard films that we were using, and we would find the nearest window and hold these x-rays up so we could read them. And you compare that to the environment that we have here at MD Anderson and many other centers around the country. This is our intraoperative CT scanning room, and we use this with the stereotactic navigation system, as you can see here, and we're able to do very complex surgeries and complex imaging using these resources, and you can see some of the 3D reconstructions that we've done in the past. So I learned from that, those experiences, that medical technology is not something to take for granted, and started to really ask my question, what is this thing, innovation, and how could I get involved? And started to really think about just the basic definition, and it's really clever ways to introduce new things into the world, and hopefully we're making it better, right? And then I started to study in my space some of the surgical innovators, and started to learn, about them and their areas of interest, and what they've done for our field and for humanity. And this is one of them. This is Dr. Gluck. And what you're seeing here is a write-up describing the first knee arthroplasty. And this was made out of ivory. And here you can see some x-rays of a patient who had both an ivory implant and then a metal implant. And so it's very interesting to read about these pioneers in our field of joint replacement, and to think now how many joint replacements are being done and how many people are benefiting from them. But it started, with some really basic principles and technologies. When I was a resident, we were planning our surgeries using, the plain films and these templates. As you can see, we would overlay these outlines onto the X-ray, and we would plan out the size of the implants, And that would be then how we got our implants ready for the surgery. And today we have much more sophisticated software that we can use to really do a much better job of planning the surgeries and capturing that information. We also have to think about the advances in imaging. And again, we owe a lot to folks like these gentlemen here and what they did for developing MRI. And you can see this MRI of the spine, really great detail that you can use in terms of making a diagnosis and coming up with a treatment plan. And part of the process is differentiating the structures. And in the cancer world, we obviously want to identify what is cancer and what's normal structure, and how we might need to treat this and surgically remove these. And so I've learned a lot about this process and spent a lot of time with our experts in the radiology space and also in the medical illustration areas. And we applied this to a patient that had a very complex tumor that you can see here on the MRI and the clinical photo that draped over the cervical and thoracic spine. And so this was a really challenging problem because of the location of the tumor and the structures that were involved. And so we really had to think through the approach to this patient. And as I got more pulled into this to just take care of the patients, started to learn more about the underlying technology and the Stl file. And that's, you know, the language that the 3D printer is speaking and reading to give us the objects. And so I just want to quickly talk about some of the ways we use these Stl files in surgery. And so we use these anatomic models, and we have a great 3D printing lab in-house, and you'll hear more about that. But these models are very useful in planning out the surgery, talking to our multidisciplinary team, talking to the patients. There are many different applications for them. We also use 3D printing for these cutting guides. And so if you can imagine, if you wanted to cut a straight line along the board, you can draw a line, or you could also put a piece of scrap wood on that board that you run your saw along to make that straight cut. And that's kind of what we do with these cutting guides. And so these are 3D printed guides that you snap onto the anatomy, and you run your cutting tool on the edge of that object, and that gives you the line that you want. And that was helpful in this particular case. A young lady that had a osteosarcoma of the back of her femur. We were able to do the surgery using these guides without removing her entire knee joint and replacing it with a big endoprosthesis or metal implant. We also found that we're able to use the Stl file and use that in our navigation system to create virtual cutting guides. And then we're also able to create 3D custom implants. And here's an example here. So just to take you through some of the cases, sarcomas are the types of tumors that we treat in orthopedic oncology. And these are really bad cancers of the musculoskeletal system. And here we see some examples. This one is a cancer involving the brachial plexus. This was a cancer, sarcoma involving the scapula. So this is the glenoid that we're seeing. And then this is an MRI of a pelvic chondrosarcoma, and this is the resected specimen. This is some gross examples of the specimen. These sarcomas can spread throughout the body and cause pathologic fractures, as you see here, and then go to other organ systems such as the lungs. And our goals are to remove them completely. So we want a negative margin, and we also want to optimize quality of life and function. And so the question is, how do we remove that terrible cancer that we see here on the MRI involving the pelvis, the right side of the pelvis and the sacrum? How do we do that safely, and how do we maximize the function? I I mentioned our intraoperative CT room. This is a couple pictures of the CT scanner on rails, and that's going over the patient for the scan intraoperatively. We then push that information to our navigation system and use those that data set to navigate the patient's anatomy. And here you see the spheres on our tools, and it allows us to see the tools in the patient and use that information to safely place implants and make cuts of the bone, as you can see here. We've adapted a cutting tool with the arrays that allow us to cut precisely and save critical structures. And so very useful technology. And I just walked through a couple of the ways that we're using these models. Here we see we get our advanced imaging, we'll do our segmentation process, and then we define the relevant anatomy in the STL file. We push that to the 3D printer, and Dr. Tapa will talk about that in a bit. This particular case, we looked at that clinical photo with the tumor on the back of the neck and the upper thoracic spine. This was a 2-day surgery where we went front and back. This model was extremely helpful because we had to go through the sternum. And one of the things I wasn't sure of was whether or not we were going to be able to get our surgical tools into that space and actually be able to make the cuts that we needed to make on the pedicles. And so we did a life-size model, and that allowed us to take measurements and practice with our surgical tools. And that during that process, we confirmed that we were able to do the surgery as we had planned it. And these are some of the intraoperative photos. There's the sternotomy, and we're looking at the mediastinum. This CT scan shows the opening, and this scan shows the cut that we made from the front through the pedicle towards the spinal cord. This is day 2, and here we can see in this image here, there's the cut that we made the first day. And these were multiple cuts in the pedicles. We made cuts on the other side, and then this came out on block. And these are some of the intraoperative photos here with the resected specimen and the post-op scans. This is just another case. This one is a sacral chordoma, a very large sacral chordoma involving the most of the pelvis and extending into the soft tissues. And so we made a model here. You can see the posterior view and then the anterior view, and this is next to the resected specimen. This was again very helpful in planning the surgery out and the reconstruction. As you can see here, this is the lumbopelvic stabilization and the rectus flap that was performed by Dr. Mericli. And here is the patient and the postoperative scans. He fused his vascularized fibulas, and here he is walking into clinic for a post-op visit. So again, very useful in terms of planning out our surgeries and executing them. The 3D cutting guides are same process initially, but we're making a guide instead of the model. And this particular picture, this guide is placed on not only the patient's a diseased anatomy, but also a cadaveric specimen that we then placed as a allograft. And this is the MRI. You can see the modeling that we did, surgical planning, and plan the cuts. And then this was created by a company that we use, Oncos, to make these cutting guides and the implants. And so this is the intraoperative photos, and this is the resected specimen, and there's the reconstruction. And these are the post-op CTs, which show the healing through the allograft. The next application is the virtual cutting guides. In certain scenarios, we're not able to place a physical guide. There's just not enough real estate, not enough space for the guides to go in. And so we learned that we're able to push that STL file to the navigation system and overlay these objects onto the intraoperative scan. And here we see a case, this gentleman had a chondrosarcoma in the back of his sacrum. And typically a high sacral lesion requires a front-back exposure. We need to get into the front of the sacrum to release the vessels and the lumbosacral trunk, and then we go posterior. But in this case, we used the virtual guides, and we did this all through a posterior-only approach to a small incision. Here you see the virtual guides. We've created these objects in different colors so we can run our cutting tools right on the line that denotes the tumor side versus the normal side. And then this is the intraoperative picture, very small space, but because we're using the advanced imaging, it's very reliable and safe. And here's the resected specimen. This was another case of very extensive sarcoma in the lumbar spine and sacrum. Again, modeled this using cutting guides, and this was vascularized fibula reconstruction with both fibulas to create a stable junction between the lumbar spine and the pelvis. And these are some of the intraoperative photos, and this is after the resected specimen has been removed, and you can see the instrumentation here and the defect. And then this is the X-ray after the fibulas have been placed. And actually this is 15 months later, where there's healing between the fibulas and the pelvis. So very useful. And in the last case, just to show the 3D printed model, the 3D printed implant that we use to reconstruct this defect in the lumbar spine. This model here shows the implant that we would use, and this has a docking site for a vascularized fibula. And so a very unique custom implant. This was a multi-day surgery with multiple surgeons, and this is the resected specimen. This is the implant and the vascularized fibula, and these are the CT scans. So many different ways to use these technologies, from the models to the implants to the virtual guides. And I think we still have a long way to go, and still a lot of challenges. And so we're excited to work with our innovators in all the different specialties, including diagnostic imaging, and really appreciate the efforts that have gone into developing these technologies. We've also created a lab here at MD Anderson to move these technologies along and validate them, and that is the Ideas Lab. And these are some of our physicians and some of our team members that have helped us along the way. So I will stop that there and say thank you, and turn it over to Dr. Santiago.
Thank you so much. And I think we have to really for his part of his experience.
All right, I'm just going to share my screen. Okay, can everybody see that?
Yes.
Okay.
Yes.
So, so my name is Alexander Mericli, and I'm a plastic surgeon at MD Anderson, and I have the distinct pleasure of working a lot with Dr. Bird with these complex cases, and really appreciating the intersection of 3D printing technology and surgery. And what I'm going to talk about today, though, is not so much how we use 3D printing in the OR, but how we innovate outside the OR in non-clinical applications. I'd like to thank Dr. Santiago for inviting me to present today at this panel, and also the Radiological Society of North America for having me. These are my disclosures. So we're gonna just talk in general, why one might want to innovate as a physician, and then my kind of personal philosophy as it pertains to innovation, the impact of local resources such as the Ideas Lab that Dr. Bird mentioned, really the brainchild of many years of work on his behalf that all of us here at MD Anderson are able to benefit from. And then some of my own current innovations. So, you may have noticed that I am a plastic surgeon, and plastic surgery has a rich history of innovation within the specialty itself. And I think there's a number of reasons why that's true. I think the specialty itself tends to attract people that are a bit more creative, maybe than the mean. And also we have the privilege of operating outside a specific anatomic area or organ system. Really, we operate around the whole body. And that also, I think, nurtures a certain degree of creativity. The other thing that is nice is that as a reconstructive surgeon, we have the opportunity to operate and collaborate with a number of other different surgeons and physicians from a wide variety of clinical backgrounds. And that, I think, fosters a cross-pollination of ideas that helps to support innovation within the operating room. Historically, there's a number of innovative firsts that have been enjoyed by plastic surgery. The first kidney transplant was performed by a plastic surgeon in 1954 at the Brigham Hospital in Boston. Dr. Joseph Murray actually won the Nobel Prize for that. The adult adipose-derived stem cell was discovered by a group of plastic surgeons, and at least 2 plastic surgeons that I know of are on the patent for the adipose-derived adult stem cell. Harry Bunkey is a hand surgeon and a plastic surgeon, and he is credited with developing microvascular reconstruction and microvascular anastomoses. And here he is pictured after performing his first thumb replantation. Liposuction, obviously developed by plastic surgery, not only the technique, but all the instrumentation and technology that goes along with it. And now it's the most common aesthetic plastic surgery procedure performed worldwide. And of course, the darling of the media, the breast implant, invented by a pair of plastic surgeons in Dallas in 1963, Cronin and Giroux. So I think a number of personality traits are important when it comes to somebody that is an innovator. And I think the keystone of the personality traits that one must possess is just an innate sense of curiosity. Why things are done the way they are, if there's a particular reason for that, and if there's a way that things can be done better. I think certain groups of people have this kind of built into their psyche, and I think at the heart of any innovator is curiosity. Other important characteristics, and this is by no means an exhaustive list, but just an appreciation for problem solving, and then also an interest and appreciation for entrepreneurship, I think also goes hand in hand with innovation. This is one of my favorite stories about, at least I like to think of it as being related to innovation. And it's also a very important characteristic that one must have when they're setting out to solve a problem. And that really is kind of the idea or the concept of thinking outside the box. In World War II, a group of military engineers noticed that the planes that were coming back from battle had very distinct groupings of bullet holes around them. And so their commanding officer asked them to kind of use this information to design a better armored plane. And so at first, the engineers thought, well, these are the locations where the planes are most likely to get hit by bullets And so we should be, armoring these areas extensively so that we can have the bullets deflected when the plane is hit in this area. But then another engineer thought, well, maybe actually these are the planes that we're looking at, the sample size that we're using, these are just the planes that have made it back from battle. So maybe this is these bullet hole groupings, this is where planes can sustain a bullet hole and still be capable of flying back to the base. So maybe we need to think about this exactly the opposite. And that's actually, in fact, what happened to be true, because if you look in the areas that don't have these bullet hole groupings, these are the cockpit, the engines, the fuselage, and then the midsections of the wings, which is where these planes would hold their bombs. And so if a plane were to be shot in any of these areas, it was more likely to crash and never make it back to the base. So really the key innovation here was not to armor the areas where the bullet holes were observed, but actually the exact opposite. There's been many textbooks written about innovation and kind of trying to assign a scientific method to it. In general, there's kind of three phases. Conception, which is when the idea is kind of generated and planned out. And then the implementation phase, which is where 3D printing really comes into play and is an important tool in this phase of the innovation process, because it allows us to take an abstract idea and turn it into a concrete prototype that can be then used for pilot testing. Also is important for demonstrating to others what the idea is, because it's very difficult to communicate verbally without a visual aid. And that in turn is important for obtaining investments if this is something that is to be commercialized. And so really 3D printing is an invaluable tool for this stage of innovation, because before 3D printing, this stage was very expensive and onerous and really had to rely upon machining, custom milling, injection molding techniques to make prototypes, which are very cost prohibitive. And now with a much less expensive device, the 3D printer, we're able to rapidly innovate and make incremental changes in prototypes in order to come to the final product. I became comfortable with the concept of 3D printing through my clinical work. As Dr. Bird alluded to, I do a lot of these reconstructions that require vascularized bone as a plastic surgeon, both within the craniofacial anatomy as well as in the pelvis and the extremities. And so I was very comfortable using this technology in the clinical realm. And so when the Ideas Lab came to be, due to the hard work of Dr. Bird and others, I was able to kind of easily transition into using 3D printing in more of an investigative situation. And so I wanted to talk to you a little bit about some of my projects that I've done in collaboration with the Ideas Lab. The first is during the height of COVID-19, when N95 respirator masks were difficult to find. We were able to use our 3D printing technology in order to figure out a way to 3D print an adapter that would allow us to use a typical scuba diving mask as an N95 respirator. So in place of the snorkel, this adapter would be placed, and then a very small surface area of N95 material could then be placed on this adapter. So functionally, it allowed us to turn one N95 mask into 5, because that's how many, if you cut the N95 mask into 5 different pieces, they could be used in this adapter, and then the scuba diving mask could just be sterilized and between uses. The next is an idea that was brought up by one of our neurosurgeons. Neurosurgeons use drills and burrs a lot to contour the skull, and that creates a lot of bone dust which not only gets in the way surgically, but has, unknown ill health consequences if it's inhaled. And so usually this is suctioned during the case to prevent aspiration of the material. But he was exclaiming, why don't we have a device that allows the suction tubing to just be in continuity with the drill, and that way I don't have to have an assistant hold the suction. And so we developed this very simple clip device here. One end of the clip clips to the drill, the other end clips to the suction tubing, and that way there's a suction device directly adjacent to the drill bit, which suctions up the bone dust as it's created. And these are little tiny innovations, little tiny tools that, if it weren't for the Ideas Lab and the 3D printing technology that is afforded by it, it probably the concept probably would have began and ended in the operating room as just a one-off comment. But now we can very easily take this idea and generate it into an actual device. The thing I'm going to talk about the most is the innovative device I've kind of put the most work into and have been working on the longest. This is the clinical problem, ventral hernia repairs. So when an abdominal hernia develops, it's typically repaired with a mesh reinforcement, and the mesh is secured to the periphery of the abdominal wall with multiple sutures that are placed in a very painstaking, tedious fashion. And this part of the operation can take 40 minutes by itself, and it's also physically difficult to place these sutures. They oftentimes will cut through your gloves, can even cut your fingers because it's very hard, very firm material. And so I thought, wouldn't it be nice if we had some type of a surgical rivet or a fastener that could be used in place of the sutures to secure the mesh? And this sounded like a perfect job for the Ideas Lab. So I kind of went and started brainstorming, and I was working on my car at the time, and I noticed these plastic fasteners that are used to secure the bumper to the car and the fenders and that sort of thing. And I thought maybe this design could be used in the human body to secure mesh. So I sketched out my idea in a notebook here, and you can see the picture of that. And I filed an invention disclosure report with the university just to kind of put my stake in the ground for this idea, and had a meeting with the Ideas Lab Biomedical Engineer, and she's unfortunately moved on to a different opportunity now, but she really helped me kind of work through this back of the napkin drawing and create a device. So we came up with two designs, design A and design B, and you can see here kind of the initial prototype on the left and the timeline, how it kind of developed from one idea into the next. And what 3D printing allows for in this situation is rapid iteration. So these changes can be made very quickly, and you can quickly innovate and come closer to the final version of the device. Now, what we did after this phase is we submitted, and this is just some of the CAD drawings, and then the actual 3D printed prototype that was created from the CAD drawings. There's design A and then design B. And when design B, it kind of compresses on itself and it deploys these wings that sandwich the mesh to the human tissue. This is the picture of design B after it's been deployed. And here's a video of the way design B works when it's deployed. So you can imagine mesh and human abdominal wall tissue being sandwiched there between those two portions as it's compressed. So what we did next is we, with the help of the Office of Technology Commercialization at MD Anderson, we submitted these two designs to an outside patent firm, and they did an exhaustive patent search in order to help us develop our IP strategy. And what they concluded was that design B, the one that I just showed you a video of, was much more likely to be successful for a patent. And so that allowed us to focus our efforts on further iterating and further improving the design of prototype B. And we let kind of prototype A fall by the wayside. So this is prototype B being tested in a cadaver. You can see here with a piece of surgical mesh being secured to the human cadaveric tissue, how that works. Here's the internal surface of the device, and then the surface of the device that's on the superficial aspect of the abdominal wall musculature, but still underneath the skin. And this is just demonstrating the tensile strength that the device has, able to secure the mesh effectively. So where are we now? We've secured a provisional patent for this idea, and we're in the process of filing for a full patent. And all of this rapid innovation, rapid iteration of this device, I think can be the 3D printer as a tool can really be credited with our success. So in conclusion, I think innovation and creativity is an important motivator for many physicians, in particular those with academic roles. And if a facility can develop an in-house 3D printing program, it really is an invaluable tool to assist with rapid vetting and iteration of ideas and prototypes that would otherwise probably be ignored. So thank you for your attention. And this is my email address. I welcome any emails that you might have. Please feel free to email me directly. And this is my Twitter handle. I'm embarrassingly inactive on Twitter, but that's it if you feel like looking me up. So thank you again for your attention, and I'll pass the mic now to Dr. Tappa.
Let me start sharing my screen. Can you guys see my screen?
Yes, thank you.
All right. Thank you for the introduction, Dr. Santiago. Hello, everyone. My name is Karthik Tapa. I'm a biomedical engineer. I'm working as an anatomic 3D specialist over here in MD Anderson Cancer Center. I would like to thank RSN SIG for giving me this opportunity and having me here. I would like to briefly go over some of the important aspects of prototyping. I'll be talking about importance of communication between a provider and a biomedical engineer or a designer. I'll also be talking about some of the aspects you need to account while designing a functional prototype, how you can optimize the designs for 3D printing, and I'll be talking about choosing the right material for the right application, with emphasis on importance of the feedback for future iterations once the prototype is delivered. When a provider reaches out to you for designing or 3D printing a prototype, it is absolutely necessary to gain much information about the intended prototype and its applications. From my personal experience, I can strongly say that more I know about the project, better I can help achieving the goals. Providers may or may not know about the 3D printing technology. So it's always helpful to let them know your capabilities, show them some of the previous models and prototypes which you have already worked. These are some of the questions you need to ask before you begin working on designing or 3D printing. The important question here is the prototype being, is it just in the form of an idea, or is it in the form of a 2D diagram on a paper, like Dr. Mericli was showing, or do you already have a prototype and looking to improvise the prototype? Then ask about the different aspects for the prototype where it is lacking and how you can betterment these lacking aspects. Knowing the functionality is essential. Like, does the prototype bear load continuously, or does it have to be extremely strong and tough, or does it needs to be very flexible, pliable, at the same time be durable? Questions like these will really help you achieve the goal quicker. The functionality of the prototype goes hand in hand with the material selected. I'll be talking more about this. Communication between both the parties, a service provider and a designer or a biomedical engineer, is very essential and is crucial. For new providers, it helps to learn the capabilities of the 3D printing technologies. And for returning providers, it aids in improvisation of the process and prototype. So here are the images of anatomical models requested by our thoracic and cardiovascular surgeon, Dr. Ara Vaporsian. In OR, when the tumor is resected along these marker lines, reconstruction is done using plates. So Dr. Vaporsian has been using these anatomical models as templates to pre-bend the plates in order to achieve exact curvature of the ribs and determine the dimensions, the geometry of the plates, as well as save time in OR. So when we first made the model for him, we wanted the model to be very precise, have every minor detail on it. But as you can see in the image too, the model is very rough, very raggedy, shaggy. Although we applied the booling, we smoothed the product out, we wrapped it, but we did not do it enough. We wanted to preserve as much detail as possible. But Dr. Vaporsian could not use this model. He had trouble bending the plates because of the bony structures and rough surface. He had to smooth out manually some of the areas and then pre-bend the plates. So from his feedback, we learned that having a smooth surface onto the ribs without changing the curvature of the ribs will be really helpful for pre-bending the plates, and for his serves well for his purpose. And in the last image, you could see our recent model where we have smoothed out the ribs without losing their curvatures, with still holding the rib surfaces together. So these models will be really helpful for pre-bending the plates and better than the previous model. So here are the images of prototypes we 3D printed in collaboration with the Ideas Lab. In the first prototype image, you can see that both the ball and the socket have larger diameters at the center. And so it required extreme pressure to plug the ball into the socket. So it was also hard to remove the ball once it is plugged in, and sometimes the socket breaks on application of pressure. So just making little tweaks to the design, like here in this image, you could see adding the streak lines, cut lines, and changing the material from extremely rigid resin to a durable resin has solved the problem. So be mindful of the design. Feel free to make minor changes, although if those changes, if they are not affecting the functionality or the design of the product. Majority of the prototypes fail due to the fatigue or stress. Identifying these fatigue points or the stress points early on will aid you in reaching the goal or making the prototype sooner. Some of the aspects you can consider while designing prototypes prone to this fatigue and stress include avoiding sharp edges. So instead of having a sharp edges, you can use bevel surfaces, and also avoid abrupt changes in the cross sections. Instead of going all the way from 100 to 50, you can use a gradient going from 100, 75. So use a gradient if you want to change the cross section. Select materials which have good fatigue properties. So when you select a rigid, tough material for load bearing, they tend to crack, they tend to break. So instead choose a durable material where it still has a good Young's modulus and it can withstand a slight bending and will not break as easily. And also always avoid having thin walls and thin edges. This is where the crack propagation starts, and then the whole prototype tends to break down. So for centuries, subtractive manufacturing has been very dominant, and most of the rules we find for designing are laid according to the subtractive manufacturing. So we need to start thinking differently. Here in these images, you could see that the printed product in the first design have only one joint right at the bottom, attaching the parallel sections of the U-shaped curve. Um, so when this model is 3D printed, it was mechanically not stable and it warped on sterilization. So a simple change in the design, instead of removing the joint at the corner to the open ends and sterilizing or printing with a different material, has solved the issue. So before hitting a start button, always think if the design you did is foolproof, or do you see any issues with the design? So to best understand the additive manufacturing, we also need to understand the process of additive manufacturing. Here are the images of hollow bladder sliced according to the additive manufacturing technology used. Top three images show the support material being laid within the hollow model. And if required design corrections are not accommodated to these models, removing the support would be cumbersome. Just by adding vent holes to the design as shown in the bottom image, bottom first one and third image, you can see that the support removal is easy. If you're using a PLA or dissolvable PVA or dissolvable FDM support material, so adding just those holes can help you remove the support materials, and same thing with the polyjet too. But in the case of SLA, you do not have any dissolvable support materials. So you need to split the model into two, print it up with the supports, remove the supports, and join the two halves. So choosing the right technology for right application is also important. If it is okay to have a seam along the length of the model, and if it would not affect the functionality of the model, then go for the SLA here, like in this case. Or if it is okay to have tiny holes on the model at inconspicuous locations, then go for the FDM or polyjet 3D printers. Like every technology has its own challenges with the use of the support materials. Here are the listed some of the key points with respect to the supports with all the three different technologies. We should note that for the FDM, the material which we use for dissolving the supports is expensive when compared to the model materials. Say if you are using a PLA or ABS, these materials are cheaper than the PVA, which is resolvable support. So be mindful of using the PLA. If the, like I was saying before, if the model can accommodate a two-part model without using a support material, go for it. It will save you the cost on the support material, as well as it will save you the post-processing time. Unfortunately, SLA does not have any dissolvable support materials. Although polyjet printing machines, they have their support material is cheaper than their model material. The material cost itself on the polyjet is more compared to the FDM and SLA. I cannot stress enough about this. Material selection is crucial for the success of a prototype. Depending on the application, some of the important characteristics to consider include strength, durability, flexibility, weight, resistance to heat, corrosion, if it is sterilized, ability to cast, machinability, and conductivity. So before hitting a print button or before choosing a right material for the application for printing or making a prototype, you need to consider these essential characteristics of the material as well as the prototype you intend to have. So these are the images of the test tube stands used by the behavioral science department people to determine the nicotine levels in the human samples. In the first images, you could see they have used a local vendor to laser cut a cardboard sheets and then assemble these cut parts into a test tube stands. When these people learn about the in-house 3D printing technology, they reached out to us, they provided these models to us and asked if they can replicate these models in-house and 3D print these instead of they going to a third-party vendor outside. So we could successfully 3D print these just like what they wanted without us knowing the application here, what they are really doing with the test tube stands. All we know is they are putting the stands, test tubes into the stand and they are testing the measuring. So after we providing a couple of batches of these test tube stands, when we asked for the feedback, they have provided images of the test tube stands with the gradient strip where they put in the gradient strip along with the test tube stand and then measure the gradient and determine the amount of nicotine present in the human sample. So once we saw these test tube stands, we reached back to them and we requested if the design can be changed, design can be improvised in order to save time on printing, save the material and save the cost. Once we made the redesign the whole test tubes and they tested out these test tubes, we could save here, you could save that around for printing the previous test tube stands, it took around 1 hour 15 minutes, whereas for the new redesigned test tube stands, it only took 44 minutes. And the material used for the previous stands were only 7 grams, and for the new stands, it only used 5 grams. So once these stands were successfully redesigned, we started bulk manufacturing these, and we are still continuing doing the 3D printing. Thank you. This is my email ID. Please feel free to shoot me an email if any questions.
Well, just want to say thank you to all of our speakers and their wonderful contributions. We have a quick question from the chat for Dr. Tapa. They would like to know how you smooth the surface of those ribs for the 3D printed model.
So here in MD Anderson, we use Mimics medical software. So in the software, the software is a two-part. I use Mimics medical as well as a Mimics 3matic. So partially I smooth out the ribs in the Mimics using the smooth option. Again, the smoothing completely as I've shown in the image is not possible with the just the Mimics. So I import the Mimics model into the 3matic as well. And I smooth out it. So there are options to smooth out the online surface, superior surface on the 3matic as well. So I use both Mimics medical and 3matic.
Thank you. And so we are at the top of the hour. So we are running a little bit short for questions. The last question was about the physical model, the 3D printed model in terms of this. I think the question was, how did the surgeon smooth the surface of the initial model? And they just took labor intensive
Yes.
elbow grease.
Well, again, from what we heard from the physician was not all the surfaces were rough, only in the few spots that he needs to smooth out. So He used some sandpaper to smooth out, and also I think he also mentioned a pocket knife to chip away the debris and bony structures on the surface.
Mhm. Very well. And I think our speakers have highlighted the different aspects of both direct clinical innovation as well as innovation when our traditional tools can't make it, and really engage our brain into finding answers outside the box. And most importantly, our team approach, which is critical in all aspects of medicine, and how privileged we are to have the collaboration of biomedical engineers such as Dr. Tapa within our institution. We want to again say thank you to everyone that participated and joined us for today's webinar. And again, if you're interested, you can join the 3D printing special interest group. You don't have to be a member of RSNA or be a radiologist. We welcome all the end users, and you can join our community and share your ideas there. Once again, thank you everyone for joining us. Thank you. Very special thank you to our speakers today.
Thank you for having us.
Thank you.
Yes, thank you for having us. Appreciate it.